We stopped at exercises where the first one is give a real world example that requires sorting or a real world example that requires computing a convex hull. So my understanding is that for example we have a list of cities and we need to cover a region. We need to find which are the cities which come on the border, so that can be a convex hull problem. Sorting, we see it in everyday life. For example, in shops, we need to sort it size wise or something, or name wise in the database. Other than speed, what other measures of efficiency might one use in real world setting? Other than speed of the algorithm, we need to see the correctness, how accurate the answer is. But then that comes in the definition itself. For all the input instances, we need to have correct output. So, other than speed, Hmm. How less is the size of the algorithm? How does it do the job efficiently in a lesser amount of space? I mean, we can have a multiple core processor algorithm, and we can have the same solution using an algorithm which uses a single core, which is again dependent on the speed, but also let's see, select a data structure that you have seen previously and discuss its strengths and limitations. I am not sure about it. How are the shortest path and traveling salesman problems given similar? The traveling salesman can be the shortest path the salesman takes to avoid getting tired. How are they different? I have no idea. Come up with a real world problem in which the only best solution will do, then come up with one in which a solution that is approximately the best is good enough. Real world problem is in hospitals where each measurement is only the best solution will do. We don't have time for errors there. Approximately good enough is it can be, for example, a school time schedule. It can be approximately good enough. Algorithms as a technology. Suppose computers were infinitely fast and computer memory was free. Would you have any reason to study algorithms? The answer is yes. Why is it yes? If for no other reason than that you would still like to demonstrate that your solution method terminates and does so with the correct answer. You need a way to see if the algorithm works, even if all the other restrictions are removed. If computers were infinitely fast, any correct method for solving a problem would do. You would probably want your implementation to be within the bounds of good software engineering practice. For example, your implementation should be well designed and documented, but you would most often use whichever method was the easiest to implement. Of course, computers may be fast, but they're not infinitely fast, and memory may be inexpensive, but it is not free. Computing time is therefore a bounded resource, and is so is space and memory. You should use these resources wisely, and algorithms that are efficient in terms of time or space will help you do so. Okay, efficiency. It should be in time and in space. As I said earlier, the size of the algorithms also matters, and the size it takes to solve the problem in memory also matters. Efficiency. Different algorithms devised to solve the same problem often differ dramatically in their efficiency. These differences can be much more significant than differences due to hardware and software. As an example, in chapter 2, we will see two algorithms for sorting. The first is known as insertion sort. Okay, we are encountering the first algorithmic names. Till now, they had made it too general. Insertion sort takes time roughly equal to C1 n square to sort n items, where C1 is a constant that does not depend on n. That is, it takes time roughly proportional to n square. The second merge sort takes time roughly equal to n log n, where log n stands for log to the base 2 log of n to the base 2, and C2 is another constant that also does not depend on n. Insertion sort typically has a smaller constant factor than merge sort, so C1 less than C2. We shall see that the constant factors have far less impact on the running time than the dependence on input size. And let's write insertion sorts running time as C1 n to n, and merge sorts running time as C2 n to n, C2 n log n. Then we see that where insertion sort has a factor of n in its running time, merge sort has a factor of log n, which is much smaller. Where if n is 1000, log n is approximately 10, which is, and when, okay, for intuitiveness, 2 to the power 10 is 1024, so log of 1000 to base 2 is approximately 10. Although insertion sort usually runs faster than merge sort for small input sizes, once the input size n becomes large enough, merge sort's advantage of log n versus n will more than compensate for the difference in constant factors. No matter how much smaller C1 is than C2, there will always be a crossover point beyond which merge sort is faster. For a concrete example, let's put a faster computer running insertion sort against a slower computer running merge sort. They each must sort in a row of 10 million numbers. Although 10 million numbers might seem like a lot, if the numbers are 8-byte integers, then the input occupies about 80 MB, which fits in the memory of even an inexpensive laptop computers many times over. Suppose that computer A executes 10 billion instructions per second. 80 megabytes is 80 into 10 power 6 bytes. 10 power 6 is 1 million. So 8 into 10 is 80. So that is the calculation. Suppose that computer A executes 10 billion instructions per second faster than any single sequential computer at the point of this writing. This book was written in 2009, of course, and computer B executes only 10 million instructions per second, so that computer A is 1000 times faster than computer B in raw computing power. This instructions per second is that the CPU can only execute one instruction at a time, and the number of instructions it can process per second, the faster it is. To make the difference even more dramatic, suppose that the world's craftiest programmer codes insertion sort and machine language for computer A. So what it means is that usually we use high-level languages for coding and implementing designs, but machine language is language understood by the computer, and every program in the end gets converted to machine code or binary code if that is more common to you. And this binary language code is hard to code in, but that is how previously in 1950s and 1960s people used to code using machine language. They are saying that the craftiest programmer codes insertion sort in machine language so that there is no need for assemblers and compilers and those things. The resulting code requires two n square instructions to sort in numbers. Suppose further that just an average programmer implements merge sort using a high-level language with an inefficient compiler, with the resulting code taking 50 n log n instructions. This inefficient compiler makes sense because in programming we have compiler optimization. For example, if a variable is declared but unused, the compiler may remove the variable for optimization purposes. To sort 10 million numbers, computer A takes 10 million is the n. We need to substitute it in the n. 10 power 10 instructions per second, they have given it as the speed of computer A, and 2 is the C1 constant. So this takes about 20,000 seconds, while computer B takes 10 n log n into C2 by the number speed of the CPU. By using an algorithm whose running time grows more slowly, even with a poor compiler, computer B runs more than 17 times faster than computer A. The advantage of merge sort is even more pronounced when we sort 100 million numbers, where insertion sort takes more than 23 days, merge sort takes under 5 hours, 4 hours. In general, as the problem size increases, so does the relative advantage of merge sort. Algorithms and what we read just now is about the efficiency part, how efficient algorithms make a whole lot of difference. Algorithms and other technologies, the example above shows that we should consider algorithms like computer hardware as a technology. So we study electronics, communication, computer science, computer hardware, memory chips and such things, but since we need to develop efficient algorithms even on the same machines, we need to study algorithms as a subject. Total system performance depends on choosing efficient algorithms as much as choosing fast hardware. So the journey goes like this. When you are studying algorithms, first you learn all the available algorithms developed by one of the few of the intelligent people on earth. Then you need to figure out where to use it in real life scenarios, how which algorithm to use. Then if you the next level is you develop an efficient algorithm for a new problem. Total system performance depends on choosing efficient algorithms as much as on choosing fast hardware. Just as rapid advances are being made in other computer technologies, they are being made in algorithms as well. You might wonder whether algorithms are truly that important on contemporary computers in light of other advanced technologies like advanced computer architectures and fabrication technologies, easy to use graphical user interfaces, object-oriented systems, integrated web technologies, and fast networking, both wired and wireless? The answer is yes. Although some applications do not explicitly require algorithmic content at the application level, such as simple web-based applications, many do. For example, consider a web-based service that determines how to travel from one location to other. Its implementation would rely on fast hardware, graphical user interface, wide area networking, and also on possibly on object orientation. However, it would also require algorithms for certain operations such as finding routes, probably using a shortest path algorithms, rendering maps, and interpolating addresses. Moreover, so what they're trying to tell is even when there is a high-end system with the easiest and most efficient graphical user interface for people to understand and use the application, there still needs to be algorithms in the background for to make up for uh, the users not having to use more of their brain. For example, you could just see all the routes between point A and B, and your brain is capable of seeing which is the shortest path visually. But we do need algorithms as it makes the whole process much easier. Moreover, even an application that does not require algorithmic content at application level relies heavily upon algorithms. Does the application rely fast on hardware? Are the hardware design used algorithms? Does the application rely on graphical user interfaces? The design of any GUI relies on algorithms. Does the application rely on networking? Routing in networks relies heavily on algorithms. Was the application written in a language other than machine code? Then it was processed by a compiler, interpreter, or assembler, all of which make extensive use of algorithms. Algorithms are at the core of most technologies used in contemporary computers. So what we need to understand is that algorithms, they are just problem solving tools. And anywhere there is a problem, we need a solution, we have an algorithm. Right now, it is developed for most of the technologies that we use. Most of them are efficient, but there are still places where their problem exists and the algorithms are required. Furthermore, with the ever increasing capacities of computers, we use them to solve larger problems than ever before. One example is right now machine learning is in the core upfront. Google is doing machine learning, Apple is doing machine learning, voice recognition, voice AI capabilities, translation, dynamic translation, such things. As we saw in the above comparison between insertion sort and merge sort, it is at a larger problem sizes that differences in efficiency between algorithms become partially prominent. Having a solid base of algorithmic knowledge and technique is one characteristic that separates the truly skilled programmers from the novices. That is what I am trying to aiming for. I am trying to gain the knowledge in this book so that I become a better programmer. With modern computing technology, you can accomplish some tasks without knowing much about algorithms, but with a good background in algorithms, you can do much, much more. The exercises for this section is give an example of an application that requires algorithmic content at the application level and discuss the function of algorithms involved. The application I can think of right out of the mind is Google web browser, where it needs to sort through different web pages to give accurate search results. Suppose we are comparing implementations of insertion sort and merge sort on same machine for inputs. Same machine in the sense the machine cycle, the speed, the instructions per second cycle number is the same. So the denominator becomes negligible. For inputs of size and insertion sort takes an 8 n square steps, while merge sort runs in a 64 n log n steps, for which values of n does insertion sort beat merge sort. So we can take 8n as the common here because 64 is divided by n. So the factor here is n versus 8 into log n. And for, let's say, for size, when n is 10, 8 into log 10, log of 10 is approximately 3, and this for merge sort it becomes 8 into 3, 24. Here it becomes 80. So I don't know, we need to calculate anyway. What is the smallest value of n such that an algorithm whose running time is 100 n square runs faster than an algorithm whose running time is 2 power n on the same machine? This should be faster in the sense 100 n square should be lower than 2 power n. So 2 power n crosses, we need to find a value of n such that 2 power n crosses 100 n square for n equal to 100. 2 power or n equal to 10. 2 power 10 is 1024. This is 100 into 100, which is 10,000. 10,000 is still greater than 1024. We need to find 2 power values such as that. Problems. Comparison of running times. For each function f of n and time t in the following table, determine the largest size n of the problem that can be solved in time t, assuming that the algorithm to solve the problem takes f of n seconds, microseconds. We need to calculate the value of n such that maximum value of n such that log of, for example, in the first thing, log of n is less than 1 second. Log of n is less than 1 minute. I think you can calculate chapter notes. Let us skip chapter notes, getting started. Chapter 2. This chapter will familiarize you with the framework we shall use throughout the book to think about design and analysis of algorithms. It is self-contained, but it does include several references to the materials that we introduce in chapter 3 and 4. It also contains several summations. We begin by examining the insertion sort algorithm to solve the sorting problem. We define a pseudocode that should be familiar to you if you have done computer programming, and we use it to show how we shall specify our algorithms. Having specified the insertion sort algorithm, we then argue that it correctly sorts, and we analyze its running time. The analysis introduction introduces notation that focuses on how the time increases with the number of items to be sorted. Following our discussion of insertion sort, we introduce the divide and conquer approach to the design of algorithms and use it to develop an algorithm called merge sort. We end with an analysis of merge sort's running time. Okay, whatever we studied in the last chapter about insertion sort and merge sort, those were just names. Here we are actually reading about it. Insertion sort, our first algorithm in insertion sort, solves the sorting problem introduced in chapter 1. We have a sequence of numbers. We need to have the same sequence of numbers but in an order which satisfies this condition that a1 is less than the next number and that number is less than the next number. The numbers that we wish to sort are also known as the keys. Although conceptually we are sorting a sequence, the input comes to us in the form of an array with n elements. In this book, we shall typically describe algorithms as programs written in a pseudocode that is similar to C, C++, Java, Python, or Pascal. If you have been introduced to any of these languages, you should have little trouble reading our algorithms. What separates pseudocode from real code is that in pseudocode we employ whatever expressive method is most clear and concise to specify a given algorithm. Sometimes the clearest method is in English, so do not be surprised if you come across an English phrase or sentence embedded within the section of real code. Another difference between pseudocode and real code is that pseudocode is not typically concerned with issues of software engineering. Issues of data abstraction, modularity, and error handling are often ignored in order to convey the essence of the algorithm more concisely. What they are trying to say here is that, for example, if you are trying to access an array and if the uh, element of the array is above its bound upper limit, we have an array of n elements, but we are trying to access the n plus 1th element. That gives an array index out of bound, a bound error in most programming languages. They are not trying to solve that here. We need to solve it in the program. We need to use a exception handling, error handling method there. They are just trying to introduce the algorithm here. We start with insertion sort, which is an efficient algorithm for sorting a small number of elements. Insertion sort works the way many people sort a hand of playing cards. We start with an empty left hand, and the card face down on the table. We then remove one card at a time from the table and insert it into the correct position in the left hand. To find the correct position for a card, we compare it with each of the cards already in the hand from right to left as illustrated in figure 2.1. At all times, the cards held in left hand are sorted, and these cards were originally the top cards of the pile on the table. So there are a bunch of cards, playing cards on the table. We do not know its value. We take the card at the top of the pile. We put it in the hand, and then we take another card at the top of the pile. We compare it with the card already in our left hand. We insert it wherever we want to. So the name makes sense. Insertion sort now makes sense. At the end, we have a sorted order in our left hand. We present our pseudocode for insertion sort as a procedure called as insertion sort, which takes as a parameter an array A 1 to n containing a sequence of length n that is to be sorted. Sequence is an array of n elements. Length n they have given. This is an array which contains n elements in the code. The number n of elements A is denoted by A length. The algorithm sorts the input numbers in place. This must be important. They have put it in a bold format, bold text style. Uh, it rearranges the numbers within the array with at most a constant number of them stored outside the array at any time. The input array A contains the sorted output sequence when the insertion sort procedure is finished. I guess this is what they mean by when they mean in place. The input array A contains the sorted output sequence when the insertion sort procedure is finished. They are not trying to use any other new memory location for putting all the elements. Let us try to see if we understand this figure. We have a sequence of numbers. We can call this as input sequence 1. This is the input sequence when they have given for which is an input for this procedure insertion sort. And let us go through the code. For we have picked up one card already, so we are starting with j equal to 2 to a dot length. So taking back the card example, we take the first card. We do not know if it is in order or not. The one card will always be in order. So we are starting with the second card. We already have taken one card from the top of the pile. Here top of the pile is the first element of the array. Then we take the second element of the array, or the second topmost card of the pile of cards, and we go till the end. We go through, we iterate it for all the cards in the pile. So this the first line makes sense. J equal to 2 to a dot length, key equal to a of j. Key is what they said as the element of the array. Insert a of j into the sorted sequence a, which a1 to j minus 1. What this is trying to say is we have left hand of cards, and we it is sorted. It is a sorted sequence a 1 to j minus 1. When we are taking the jth element, for example, we are picking the fifth card from the pile. We already have four cards, 1 2 3 and j minus 1. J is 5, j minus 1 is 4. So 1 2 3 4, we have four cards in our left hand in a sorted sequence. We need to insert fifth card into the sorted sequence of four cards. That is what we are trying to do here. Let us see, we have another variable I equal to j minus 1, which is the fourth card. Okay, while I is greater than 0 and u of I is greater than the key, I u of I plus 1 is equal to u of I equal to I minus 1. And A of I plus 1 is equal to the key. This thing is a loop, this while thing is a loop. I am trying to figure out what we are trying to do. So let us say we take the fifth card for example. We have a number to indicate the fourth location. We have the key in the fifth location, while I is greater than 0. So it means there is a location to begin with. I should be greater than 0 and A of I is greater than the key. So key is the fifth element. If the last element in our card in our array is greater than the key, we move the array element after the key. Okay, and that is what we are trying to do here. A of I plus 1, let us say, and let's see if we are trying to move I to the next location, and if when this condition breaks is that if A of I is less than the key. So for that instance, it doesn't move, it doesn't run these conditions, so we are copying key to. Okay, we'll read their solution now. The operation of insertion sort on an array is given array indices appear above the rectangles and values stored in array positions appear within the rectangles. The iterations for the for loop of lines 1 to 8 in each iteration. The black rectangle holds the key taken from I of j, which is compared with the values in shaded region. Rectangles to its left in the test of line 5. Shaded arrows show array values moved from one position to right in line 6, and the black arrows indicate where the key moves into the line 8. Okay, the final sorted array, let us see. For the first run, we are taking j equal to 2 to a length. J is right now 2, key is equal to 2, and I is equal to 1. We are comparing I is 1 is greater than 0 and A of I 5 is greater than 2. So we are moving 5 to a second position here. We made I equal to 0. Now for the second iteration I is not greater than 0, so this condition is false. Since this is the first location, for A of I plus 1, that is A of 1, we are putting the key there. For the second instance, j is equal to 3, k we are putting it as 4. We are comparing it with the second location. If I is greater than 0, of course I is greater than 0, I is equal to 2 there. And A of key, 5 is greater than 4. So we are moving 5 to the next location. This line we are moving 5 to the next location. We are moving I to the first position and we are again checking. But 4 is not greater than 2 is not greater than 4. So this while condition is broken, and A of I plus 1, A of the second position is given as the key equal to 4. The same thing happens in this third thing. The element is already in the sorted position. For let us see for this thing. Fifth position we have key equal to 1, and each value each of the previous values moves in this condition. A of I plus 1 is equal to A of I, since it is greater than the key. And once it comes here, I is not greater than 0, so the first position would be the key. Makes sense? Okay, we have the final sorted array, and in place we are not using any other new location, so the sorting happened in place. Loop invariants and the correctness of the insertion sort. Figure 2.2 shows how this algorithm works. For a equal to, the index d indicates the current card being inserted into the hand at the beginning of each iteration of the for loop, which is indexed by j. The subarray consisting of elements a constitutes the currently sorted hand, and the remaining corresponds to the pile of cards still on the table. In fact, elements originally in positions 1 through j but now in sorted order. We state these properties of formally as a loop invariant. So what they are trying to tell is 5, 2 and 4 and the next iteration 2, 5, 4, these were already in there in the array but now it is in sorted order. At the start of each iteration of the for loop of lines 1 to 8, the subarray A of j 1 to j minus 1 consists of the elements originally in A of 1 to j minus 1 but in sorted order. We use loop invariants to help us understand why an algorithm is correct. This point is important here. We must show three things about a loop invariant initialization. It is true prior to the first iteration of the loop. Maintenance, if it is true before an iteration of the loop, it remains true before the next iteration. Termination, when the loop terminates, the invariant gives us a useful property that shows that the algorithm is correct. When the first two properties hold, the loop invariant is true prior to every iteration of the loop. And of course, we are free to use established facts other than the loop invariant itself to prove that the loop invariant remains true before each iteration. Note the similarity to mathematical induction, where to prove that property holds, you prove a base case and an inductive step. Here showing that the invariant hold before the first iteration corresponds to the base case, and showing that the invariant holds from iteration to iteration corresponds to the inductive step. The third property is perhaps the most important one, since we are using the loop invariant to show correctness. Typically, we use the loop invariant along with the condition that caused the loop to terminate. The termination property differs from how we usually use mathematical induction, in which we apply the inductive step infinitely. Here we stop induction when the loop terminates. Let us see how these properties hold for insertion sort initialization. We start by showing that the loop invariant holds before the first loop iteration when j equal to 2, the subarray a to 1 to j minus 1 therefore consists of just the single element a1, which is in fact the original element in a1. Moreover, the subarray is ordered trivially, of course, which shows that the loop invariant holds prior to the first iteration of the loop, and the loop is a for loop. The moment at which we check the loop invariant is just prior to the first iteration is immediately after the initial assignment to the loop counter variable and just before the first test in the loop header. In case of insertion sort, this time is just after assigning 2 to the variable j, but before the first test of whether j is less than a dot length. So we are initializing j equal to 2. We then have to check in the programming language which we choose. We need to check if it is less than of length, and then we proceed, and then we uh, increment the j value. Maintenance. Next, we tackle the second property, showing that each iteration maintains the loop invariant. Informally, the body of the for loop works by moving aj-1, aj-2, aj-3, and so on by one position to the right until it finds the proper position for a of j, at which point it inserts the value of a of j. The subarray then consists of the elements originally in a of j but in sorted order, incrementing j for the next iteration of the for loop, then preserves the loop invariant. A more formal treatment of the second property would require us to state and show loop invariant for the while loop of lines 5 to 7. At this point, however, we prefer not to get bogged down in such formalism, and so we rely on our informal analysis to show that the second property holds for the outer loop. Termination. Finally, we examine what happens when the loop terminates. The condition causing for the for loop to terminate is that when j is greater than a dot length equal to n, because each loop iteration increases j by 1, we must have j equal to n plus 1 at that time. Substituting n plus 1 for the j in the wording of the loop invariant, we have that subarray consists of our elements originally in a 1 to n but in sorted order. Observing that the subarray A1 to N is the entire array, we conclude that the entire array is sorted, hence the algorithm is correct. We shall use this method of loop invariance to show correctness later in this chapter and in other chapters as well. Pseudocode conventions. We use the following conventions in our pseudocode. Indentation indicates block structure. For example, the body of the for loop that begins on line 1 consists of line 2 to 8, and body of while loop that begins on line 5 contains line 6 to 7 but not line 8. Our indentation style applies to if else statement as well. In an if else statement, if we indent else at the same level as its matching if, although we omit the keyword, then we occasionally refer to the portion executed when the test following if is true as then clause. For multivariate test, we use else if for test after the first one each pseudocode. Using indentation instead of conventional indicators of block structures such as begin and end statements greatly reduces clutter while preserving or even enhancing clarity. Each pseudocode procedure in this book appears on one page. Okay, these are just trying to tell how the code goes. If you are new to programming, maybe this would help. But if you are already if you have experience with Python or such languages, you are good to go. The looping constructs while for and repeat until have interpretation similar to the languages in this book. The for loop header, the keyword down to for decrementing this is a comment which we saw earlier. For all attributes f of an object x, setting y equal to x causes y of y dot f is equal to f dot. Since it is a pointer, okay. Pointer will refer to no object at all. In this case, its value is nil. We pass parameters to procedure by value. The called procedure receives its own copy of parameters and it assigns a value to the parameter. The change is not passing by reference and passing by value. We are not passing by value is what they are trying to say. If you are interested, you can read about passing by reference. When objects are passed to the pointer to the data representing the object is copied, but the object's attributes are not. For example, if x is a parameter of a called procedure, the assignment within the called procedure is not visible to the calling procedure. The assignment x, however, is visible. Okay, what they're trying to say is if they're passing an object, then it is passing by reference. And if they're passing a array, it is passing by reference rather than uh, passing by value. A return statement immediately transfers back. Boolean operators and or are short circuiting. That is when we evaluate the function, we evaluate okay, they are trying compiler optimization here, so that for example, and is when x and y is when if x is true and y is true, only then the output is a true. But then if one of them is false or both of them is false, the output is false. So instead of checking if when x is false and y is true or false, if x is false, the output is obviously false. So they are trying to do it. If x evaluates to false, then the entire expression cannot evaluate to true. So we do not evaluate y. This is to save time. If on the other hand x evaluates to true, we must evaluate y to determine the value of entire expression. Similarly, in the expression or we evaluate expression by only if x evaluates to false. Short circuiting operators allows us to write Boolean expressions such as x not equal to nil and x dot f equal to y without worrying about what happens when we try to evaluate x dot f when x is nil. The keyword error indicates that an error occurred because conditions were wrong for the procedure to have been called. The calling procedure is responsible for handling the error, and so we do not specify what action to take. Okay, exercises use to illustrate the operation of insertion sort, rewrite the insertion sort procedure to sort into non-increasing instead of non-decreasing. What we can do for non-decreasing is in this code, all we have to do is for the same length, we are checking if a of I is less than the key, and if it is less, so the key should come only when the key is greater than a of I, it should come to the first place. We do it, we repeat it. So for the first instance, 2 stays here. For the second instance, we have 5 and 2, then we have 4. 4 gets stuck with 2, it is greater than 2, so it goes to this location. And for the third instance, 6 is greater than 5, so it gets stuck with 2 first, it goes to 2 gets copied to the fourth position, then 4 gets copied to the third position, then 5 gets copied to the second position, and 6 gets copied to the first position. That is one thing. And the third exercise, what is the consider the searching problem. A sequence of number is given an index I such that v equal to a of a or special value null if v does not appear. We write pseudocode for linear search which scans through the sequence looking for v using a loop invariant. Prove that your algorithm is correct. Make sure that your loop invariant. Okay, we need to write an algorithm for a sequence of numbers and a value v. Consider the problem of adding two n-bit binary integers stored in two n-element arrays. The sum of the two integers should be stored in binary form, and state the problem formally and write the pseudocode. Problem of adding two n-bit integers. We can have the condition of if 0 plus 0 equal to 0, sum is 0, carry is 0, 1 plus 1 is sum is 0, carry is 1, and we can implement a full adder. Let us stop here for now.